Change in the CLC schedule. Lynn Pham has agreed to shift 2 of her previous Tuesday CLC gatherings to Friday because since our exam's on Friday in the evening, I expect many of you are interested in service at that time. So I think that will help matters. Secondly, I have a mistake in the posted CLC schedule that you see on Sakai. I'll change that this afternoon. Aya De La Rosa is only supposed to have 1 CLC period because all our 4940 volunteer instructors only get 1. I mistakenly had her typed in the CLC schedule for 2 periods, one of which was Monday 3, which is not correct. This is correct? Yeah. W6 only. So for whoever indicated that she was absent for Monday 3, I understand that. That was my mistake, not hers. Now, what I've decided to do with Quiz 2 tomorrow, because we need more foundation for such, is to have you all pick up Quiz 2 tomorrow when you leave tomorrow's lecture gathering. And since a couple of you said, for reasons I don't know about, you have to get out of town on Friday, you can finish it with ample time and bring it to my office Thursday evening. If I'm there, give it to me. If you come to my office with your worked out Quiz 2 following 7 p.m., because I'll be here till 7 p.m., put it under the office door. Don't leave it in the tray that's on my office door. Put it under the office door. And make sure your discussion instructor's name is on that. And I'll see to it goes to the correct discussion instructor for grading. For the bulk of you, most of you for sure, when you pick up Quiz 2, as so indicated here, you can turn it in accord with what I've just said, or more simply, turn it in Friday when you appear for our class gathering. Friday at the top of class, I'll have here 6 different labeled sheets of paper. The 6 different labels will be the names of the 6 different discussion instructors we have. So that when you turn in your quiz, you can put your quiz on the sheet which bears the name of your discussion instructor. And if you put it on the wrong sheet, I'm taking off 3 million points. How's that? So this way we got plenty of time to get at stuff which I want this second quiz to deal with, which goes through Introduction to Chapter 19, with which we will wrestle tomorrow, given that we got 2 class gatherings tomorrow. Your discussion gathering plus our lecture gathering, including conversation on Section 19.3. Now, what's in Section 19.3? It's a detailed discussion of something which we've already done, but not extensively. And that is, if we have an equilibrium reaction, this is Section 19.3. You can peek at it now if you want. If we have an equilibrium reaction for which the K value is not given, that means you can't look it up in a table because it's a complex K. It's composed of 2 or more fundamental equilibria. How do you get the K value? What you do, and this is what's illustrated in Section 19.3 and what we'll be discussing tomorrow, is to write this equilibrium reaction in terms of the fundamental equilibria of which it is composed, and then apply arithmetic to the K values for each of these fundamental equilibria, and calculate K for this overall equilibrium reaction. Now, what kind of equilibrium reactions have we so far considered? KW, KA, KB. And what will we introduce you to tomorrow? KSP. So whatever the composite K is, it's got to be a blend of KW and or KA and or KB and or KSP. two or more of these fundamental equilibria, for which you will have the value. Because we'll always be dealing with acids and bases, which are in the acid-base table, and KSP values, which are for materials of limited solubility in water that appear on the acid-base table. I mean on the information sheet, pardon me. All right. On we go, chapter 18. Yesterday, I inadvertently forgot to make some comments on how to deal with question 1854, but you ought to know how to deal with this, because we laid foundation for calculation of hydronium ion concentration for a water solution of a weak polyprotic Bronsted acid, which is molecular, like phosphoric acid. That's what question 1854 is about. Now, one reminder, please, in doing this arithmetic, in doing this calculation, use the K values that you see for phosphoric acid, Ka1, Ka2, Ka3, that are in the information sheet. Because those are the latest, and I presume more accurate K values relative to the ones that you see in the typed notes, as I haven't had a chance to redo the notes. I'm working on it, but it's a long, drawn-out, tiresome, time-consuming procedure. Now, to review, you recall for a weak polyprotic Bronsted acid, which is molecular, you only have to consider Ka1 to get the hydronium ion concentration. So from Ka1 for this solution, which is 6 molar to 2 sig figs phosphoric acid solution, you'll calculate the hydronium ion concentration. What do you get from Ka2? Ka2 is a number that's equal to the concentration of the species produced when the parent acid loses 2 H pluses. Okay? So Ka2 equals the molarity of this. And what are you going to get from Ka3, since this question says calculate the phosphate ion molarity? Well, Ka3 is the only equilibrium which for this system contains phosphate ion. So clearly you've got to deal with that equilibrium. So, what are you going to have for Ka3? How will it appear chemically? That's how it'll appear chemically. The ionization of this thing with water, producing hydronium ion and phosphate ion. That's the source of phosphate ion. This value you look up, that's in the table. This value you got from Ka1. And this is equal to what? Ka2. Done. So you got one unknown. And the correct value, I think the value reported in the notes is 1.3 times 10 to minus 19. With the different equilibrium constants that I'm asking you to use from the information sheet, you get 1.4 times 10 to minus 19. Not much change, but a little bit. Did I write that over there? Yeah. That's what you'll get if you do the arithmetic in accord with the directives. If you do the arithmetic correctly in accord with the directives. Enough said on that. Now let's go back to our much more fun and games issue of hydronium ion molarity computation for a water solution of a hydrated metal ion, where the main difference, chemistry of the water solution of hydrated metal ion compared to the molecular polyprotic acids, is that there is not much difference in magnitude between Ka1 and Ka2, which were rationalized from a Coulombic standpoint yesterday. Upshot, in continuing with calculation of hydronium ion concentration for our 100th molar to 2 significant figures iron nitrate solution, is that you will likely have to incorporate Ka2 arithmetic into your computation. Indeed, for this solution, you certainly do. Well, that creates a problem algebraically. Because since you've got to consider both Ka1 and Ka2, this becomes an unknown, this is an unknown, this is an unknown, and that's a remaining unknown. So you got 4 unknowns and only 2 equations. So as we noted yesterday, this requires you to develop at least 2 more simultaneous independent equations composed of the same set of unknowns. The first such equation is material balance for iron. That follows directly from the label on the bottle. Oh, here it is. This tells us that total moles per liter of dissolved iron is 0.010 moles. So 0.010 is equal to the equilibrium molarity of this form of iron in solution plus the equilibrium molarity of this form of iron in solution plus the equilibrium molarity of this form of iron in solution. Which again shows us the meaning and importance of material balance consideration. But we're still short 1 equation. So we need 1 more equation. And as we noted yesterday, by application of the principle of electroneutrality, we can write a remaining 4th equation based on charge balance for the system, which again, I repeat, is an equality established between total moles of positive charge and total moles of negative charge. Because any bulk chemical system containing charged particles, to be stable, must be equal in positive character and negative character. So with that, we can write the charge balance expression for this solution. Here it is. 3 times the molarity of iron plus 3 plus twice the molarity of iron plus 2 plus the molarity of iron plus the molarity of hydronium ion. Of course, hydronium ion is in there, and that's what we want to get, is equal to the sum of the molarities of the negative ions in the pot, nitrate ion and hydroxide ion, which can be set equal to the charge sum value of 0.030. Now, which part of this puzzle don't you understand first? Is it the charge sum, or is it how did we write this equation in the first place? Well, let's take a look at the charge sum. For starters, is this solution acidic or basic? Acidic. Considerably acidic. So, from the label on the bottle, we see that the nitrate ion molarity in this solution is equal to what? Nitrate ion molarity. 0.030, isn't it? This formula tells you, you dissolve a mole of this, you're putting 3 moles of nitrate ion in the system. So if you dissolve 0.010 moles of this, you put 0.030 moles of nitrate ion per liter into the system. And the system is acidic. So whatever the molarity is for hydroxide ion, it's considerably lower than 1.0 times 10 to minus 7. And if you add any number which is a good deal smaller than 1.0 times 10 to minus 7 to 0.030, are you going to change this? Not one damn bit. So there's where the charge sum comes from. And should we need this? Because numerically this is negligible. But should we need this? Is this another unknown? Is this another unknown? Why not? How can we get this from any of the other terms that are already in this expression? How about this? That always takes care of hydroxide ion molarity. Or vice versa, if you want the hydroxide ion molarity, and you can substitute for hydronium ion molarity. Now then, how do we write this equation? Let's take a simple case to illustrate the point. 1 molar calcium chloride solution, for which the molarities of the principal species are obviously calcium ion 1 molar, chloride ion 2 molar. Okay? Follows from the label on the bottle. What arithmetic must I do to establish equality between these molarities? I got to double the calcium ion molarity, don't I? Watch, it's really tough now. 2 times 1 is 2. Now what does that involve from a species standpoint? It involves multiplying the molarity of this species by its charge magnitude. And that's where these multipliers come from. So once you identify the positive and negative ions that are in the system and write down their formulas, and establish summation for all the positive species, and establish summation for all the negative species, in order for these sums to equal each other, you have to multiply each concentration term by charge magnitude. And that does it. Just like we did for calcium chloride solution. This is pretty simple, really. But it is something you haven't seen before. Question 1856. Recall, if you will, in our conversation yesterday, and it's in the notes, we reminded you that this stuff, which is this stuff, is a pale violet colored species. A rather attractive pale violet. If my memory's right, it rather resembles the color of amethyst's gem. Okay. But if you examine this solution, color-wise, if you make this solution, it will not appear pale violet. It will appear yellow-brown. This thing is yellow-brown in color, as is this thing. Now, number one, yellow-brown is a somewhat more intense color than pale violet. But the formula tells us that at least what was initially put in solution was the hydrated iron plus 3. So why are we seeing the yellow-brown instead of the pale violet? Why are we seeing a solution which shows the colors of this and or this rather than the color of this? Are these K values rather substantial? Are these K values numbers which are a good deal larger than 1 times 10 to the minus 7? Yes. They sure are. And is this solution fairly dilute? It's only 100th molar. So can we well expect that the extent of reaction number 1 before equilibrium is established is large extent? And number 2? So we're looking at 2 equilibrium systems, each of which are expected to react to large extents before equilibrium is established, and in so doing produce yellow-brown species. That's why the solution is yellow-brown. If any of you do any work in assignment 10 in the 46L course this term, you'll deal with 100th molar solutions prepared initially by dissolving a soluble salt of iron plus 3. Now, if you go to the side shelf in the lab and take a look, for example, at iron nitrate, the solid stuff, it's a beautiful pale violet. But when you look at this 100th molar solution, it ain't going to be pale violet, it's going to be yellow-brown. We've just explained why. Now then, just to make sure we're on top of this charge balance stuff, and before we make additional comments on how to proceed with calculation of hydronium ion molarity for this solution, let's take a look at a 10th molar solution of a different hydrated metal ion. A hydrated metal ion whose formula also appears in our acid-base table. Question number 1. In this solution, what is the principal Bronsted-Lowry acid-base equilibrium reaction? For a similar question I asked like this that was on exam 1, just about everybody got it right, so I gather you have a reasonable understanding of this issue. You see the label on the bottle. Here's the label on the bottle. From the label on the bottle and your knowledge so far of chemistry, you understand that aluminum sulfate is categorically what kind of stuff? Ionic or molecular? Ionic. And ionic compounds at the minimum always dissociate when you put them in solution. And Al plus 3 is a positive ion with a substantial positive charge density. So it will make bonds, true chemical bonds with water molecules, and become hydrated aluminum plus 3, whose formula you see in our acid-base table. Okay? That tells us why the solution will be acidic. And it also identifies the strongest acid in the system in appreciable concentration. Hydrated iron plus 3. Aluminum plus 3, pardon me. But in this solution, what's the strongest base present in appreciable concentration? What is it? Sulfate ion. So the main acid-base equilibrium is aluminum ion reacting with sulfate ion. Now, do you think that aluminum ion reacting with sulfate ion will give us a handle on calculating hydronium ion concentration for this solution if that's our test? Yes or no? Why not? Does that equilibrium have hydroxide ion in it? Does it have hydronium ion in it? Well, then it can't give us a handle on pH. Not directly so. Okay? Now then, is that an equilibrium of consequence? In other words, is the K value for that reaction a large number? Hydrated aluminum ion plus sulfate ion. Now, we haven't shown yet how to calculate these K values, but it's not difficult. Well, actually, we have. Remember when we showed you how to get the KW equals KA, KB relationship? When we had the KB for some hypothetical Bronsted base, X minus. And we multiplied it by the hydronium ion molarity, divided by the hydronium ion molarity, which is equivalent arithmetically to multiplication by 1. And showed you what that gave us. Gave us KW times 1 over KA. That's the game you're going to learn how to play in greater detail in section 19.3. Same game, just more detail. Okay. Ka, hydrated aluminum ion, 1.4 times 10 to minus 5. I'm reading it right off the table. How are you going to need Kb for sulfate ion? Kw divided by Ka for the conjugate acid of sulfate ion. What's conjugate acid of sulfate ion? Hydrogen sulfate ion. So I got 1.0 times 10 to minus 14 divided by 1.2 times 10 to the minus 2. That gives me the huge Kb value for sulfate ion of 8.3 times 10 to the minus 13. A pretty damn feeble base. Which is why 1 molar sodium sulfate solution and similar solutions have pHs which are just about 7.0, only a little bit above. Now then, material balance aluminum ion for this system, it'll be just like material balance here for the iron system, except we'll write in Al, 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 and the molarity will be, for this system, what will be the molarity?
0.020.
What's the molarity for the aluminum ion system? If I write material balance for the aluminum ion system, what number is equal to the sum of the molarities of Al3 plus quote unquote, plus Al2 plus quote unquote, plus Al plus quote unquote? What's that molarity sum equal to for this system? I'm listening. I'm listening. 0.20, isn't it? 0.20. You see that formula? Doesn't that formula tell me if I dissolve a mole of that stuff, I put in 2 moles of aluminum ion? And the numerical label is 0.10. So when I dissolve 0.10 moles of that, I'm putting in 0.20 total moles of aluminum ion. Okay? Now let's look at charge balance. We've already established how to write charge balance. Since the charge on this is 3 plus, we multiply this molarity by 3. 2 plus times 2. 1 plus times 1. 1 plus times 1. Sulfate ion, charge magnitude is 2, multiplied by 2. Hydrogen sulfate ion and hydroxide ion. Okay? And there's my charge sum, 0.60. Are you mystified by that number? You see that 10th molar aluminum sulfate solution? What is the molarity of sulfate ion in that solution? Yup! What's the molarity of sulfate ion in that solution? 0.30. And on my anion side of this charge balance expression, I have to consider twice the molarity of sulfate ion. 0.30 times 2. Ha! I get this. Is it fair to believe that the molarity of this, whatever it is, added to this will not change this at all? Is this not also an acid solution? You're damn right. Is it fair to believe that the molarity of this, whatever it is, on added addition to this, is not going to change this? Now, you really haven't seen how to tackle this quantitatively yet. But we recognize that in this system, how many reactions can account for the development of hydrogen sulfate ion? In this aluminum sulfate solution, how many reactions can account for the development of hydrogen sulfate ion? I'm listening. This is a dirty question, but I like it. In my mind's eye, I see 1, I see 2, and I see 3. How about that? 3 reactions. Do you agree that the only way we can make hydrogen sulfate ion in this solution is by protonating sulfate ion? There's nothing fancy about that statement. All we're doing is letting this damn stuff talk to us. And that's what I try hard to program you to do, because that's the hard part. I'm very sympathetic with you folks. Just because I stand here and growl and jump up and down, that does not mean I'm angry with you, which I am not. So if sulfate ion reacts with water, is water in this system? You're damn right. So sulfate ion can certainly react with water. That'll make hydrogen sulfate ion. If sulfate ion reacts with Al3+, quote unquote, will that make hydrogen sulfate ion? Yeah, we just talked about that. And the second ionization equilibrium would be aluminum 2+ plus water to give us hydronium ion. But sulfate ion is a stronger base than water, isn't it? So another possible reaction is aluminum 2+ plus sulfate ion. Will that also give us hydrogen sulfate ion? Yes? But none of these reactions are going to go anyplace of consequence, which you will far better understand when you get to section 19.3. Because in the main, what section 19.3 is going to have you learn, beside how to get K's for these complex equilibria, you're going to learn much more about appreciating what the magnitude of a K value means. This is extent stuff. So to calculate hydronium ion molarity, can I simplify this charge balance expression? Well, implicitly we're reminded you can forget this one. You think I can legitimately forget this one? I'm asking. Let's make comparisons to what we've already done up here, by analogy to this iron nitrate system. Because we recognized that Ka1 for hydrated iron plus 3 is 6.0 times 10 to minus 3. What's Ka1 for the aluminum ion? Hydrated aluminum ion. Look at the acid base table. 1.4 times 10 to minus 5. That's a lot smaller number than 6.0 times 10 to minus 3. Now let's look at the molarities. Because this aluminum sulfate solution in aluminum, what's the relative molarities, aluminum ion, this solution, compared to iron in that solution? The relative molarities of total aluminum ion to total iron plus 3. What's the relative molarities? Aluminum ion to iron plus 3. What is the relative molarities? I'm listening. 20 20 to 1. Do you see that? Let these numbers talk to you. Total iron for the top solution is 0.010 moles per liter. Right? What's total aluminum in this solution on a per liter basis? 0.20, right? Well, 0.20 divided by 0.010, the last time I checked, is 20 to 1. You've got to let these labels on the bottle tell you what they mean. No more, no less. So, we have recognized. Here we have a Ka1 value, which is a hell of a lot smaller than Ka1 up there. And here we have a molarity which is considerably greater than the molarity up there. What does that tell us about ionization extent for aluminum ion plus 3 compared to that for iron ion plus 3? Much less. Isn't that what ionization extent depends on? Ka value. Here we've got a Ka value that's a whole lot smaller. And it's inversely proportional to molarity, right? The top solution is a good deal less concentrated, much more dilute than the second solution. Both of these tell us that the expected ionization extent for hydrated aluminum plus 3 is probably negligible. Now, if you really want to prove it to yourself, you'll have to do some arithmetic. And after we get with this section 9.3, you'll know how to do the arithmetic should you be of a mind to do that. But this is legitimate. Now then, based on our simplification, how would I calculate the hydronium ion concentration for this solution? We've shown you the simplifications we can make. Now let's get at establishing why these simplifications are valid. The first issue is, as I just said, based on our simplifications, how will I calculate the hydronium ion concentration for this solution? Because what I really said here is that when I look at Ka1 and Ka2, in this case for aluminum, plus 3 in solution, do I have to pay attention to Ka2? He said, no, you don't pay attention to Ka2. So I'm going to get hydronium ion concentration strictly from Ka1. Well, come on now, that's not hard. And if Ka2 doesn't mean anything relative to Ka1 for this system, at equilibrium, how do the molarities of these two species compare? They're what? They're equal. Because Al2 plus ionization ain't going anywhere. That's what we said in making this simplification. So guess what recipe applies to this solution based on the simplifications that we have considered? Bingo. So I put in 0.020. Not 0.20, pardon me. Okay? Then I cross multiply. .20 times Ka, take the square root, I get me the hydronium ion molarity based on our simplification. Now I ask one more question. If I ask you to verify this hydronium ion concentration calculation, and I set you free in the 46L laboratory, what would you do to verify if the hydronium ion concentration we calculated by way of what we have just done is correct? What would you do? You're in the laboratory now. Tell me what you're going to do. I want to know what you're going to do. pH test. All right, a pH test DI water. You said pH test. I want specifically knowledge of what you're going to do to verify this. I'm listening. You are now my research director. And by damn, if you give me the wrong directions, I'm throwing you out. You're the boss and you failed. Well, come on, boss, tell me what to do. You're in the lab, 46L. What are you going to do to verify the hydronium ion molarity being computed by this arithmetic? What would you do in the lab? Ask your TA? Because now you're the TA. I'm the student. So you have to tell me. I'm listening. What are you going to do? Nobody knows? Well, I'll tell you what I'm going to do. I'm going to make this solution. I'm going to go to the side shelf, get me some aluminum sulfate. If it's not on the side shelf, I'll go to the stock windows. Give me some aluminum sulfate, damn it. Right now. And then per liter with deionized water being my solvent, I'm going to make this solution. Then what am I going to do? You got the gadgetry in the lab, what would you do? What would you do? Measure pH and see if the hydronium ion concentration you get from the experimental measurement on this solution equals the value we get from this calculation. That's what you do. And guess what? You'd find out the experimental value in this are the same, provided the pH meter's working properly. Okay? Wonderful. Now then, more fun. Back to this. If I ask that you proceed with computation of the hydronium ion concentration for this solution, where the arithmetic is considerably more challenging, because here you got to consider Ka2. And what are you going to look for in solving this problem acceptably? You're going to look for determination of values of molarity iron plus 3 equilibrium, molarity iron plus 2 equilibrium, molarity iron plus equilibrium, hydronium ion molarity equilibrium, and then put them into the K expressions for these two equilibria, knowing full well that when you have the correct concentration for this and this and this and this, and you put them into the corresponding equilibrium constant expressions, what number will you get if you have the good correct concentrations for these component species? What numbers will you get? For the first equilibrium, you get this number. And for the second equilibrium, you get that number, right? Because these are the constants. These are the fixed parts of the puzzle. These are the non-variants, right? Well, how are you going to go about getting these values? How would you go about getting the hydronium ion concentration? That's what I said here. Okay? Well, to my way of thinking, the best way is always the speculation way. So now we're going to show you a couple more considerations which relate to making speculations. For this particular solution, let's start with this. What's the hydronium ion concentration max? Now we're back to our iron solution. What's the hydronium ion concentration max? Tell me the value. 0.020. Anybody want to support that contention? Because this is 0.010 molar total in iron. So if this goes 100%, that establishes the molarity of this is 0.010. Aha! But there's another source of hydronium ion. And this starts out at 0.010 after the first reaction if this goes 100%. Well, if this goes 100%, then I make another 0.010. So what's the total hydronium ion max? 0.020. The sum of what I got from the first reaction added to the second reaction. All we're doing is letting these bottle labels talk to us. And what I'm trying to do is to get you to recognize how to let bottle labels talk to you. That's the hard part. So there's that. Just as we played before, we're going to see what kind of box I can put this correct hydronium ion molarity in before I start doing any further calculations. So how am I going to get hydronium ion min? Now then, for those of you who were with me yesterday during office time, we talked about this issue. And I recognize when I looked over my conversation considerations prior to this discussion, what I said to you yesterday in the office time was wrong. So let's fix it all right now. Hydronium ion min. Clearly, since Ka Fe3 plus is the biggest K value for this system, regarding, if nothing else, hydronium ion source, this reaction has got to go. Now, if I consider this reaction going, and I don't consider this reaction going, I say, forget this reaction. Let's just get us a base value hydronium ion molarity from this first reaction and no other reaction. Will I not have computed hydronium ion molarity min? Because I know I'm going to get hydronium ion from this reaction. Okay? So what I'm going to do is calculate hydronium ion molarity for this reaction and not consider at all any contribution to hydronium ion by the second reaction. That's got to give me hydronium ion min. So, to get hydronium ion min, I write 6.0 times 10 to the minus 3. And I write this. Just like we did for the aluminum ion system. Because when I write this, I am saying that when an equilibrium is established for this system, the molarity of this hydronium ion and the molarity of Fe2 plus, quote unquote, will remain equal. That means this isn't going any place. I'm treating this like a weak molecular polyprotic acid, right? That's all I'm doing. I know it's got to give me hydronium ion min, because I'm paying attention to contribution to hydronium ion by the first reaction and discounting any possible contribution by the second reaction. That's got to give me hydronium ion min, from which I get from this recipe. Now then, what do I do to proceed with this arithmetic? Specifically, to do this arithmetic, can I believe that x is negligible in the denominator? Because that's the goof I made yesterday at office time. Can I get a correct value for x for this equation by taking the square root of this number times this number? Hell no, that's not going to give me anything that's close to the correct value. I have to consider this. So what is my method for approaching this? Speculation on ionization extent. All we're doing is say, guess what? We've already talked about this, now let's put it to use. And what speculation should I try first? 50%. So let's try 50%. That gives me half of this divided by this. That's why the 50% is nothing arithmetically. Watch out, this is really hard. So from this I got 5.0 times 10 to the minus 3, but the Ka value is 6.0 times 10 to the minus 3. What does this tell me about the true ionization extent relative to 50%? The true ionization extent is what? Bigger, smaller, a lot bigger, a lot smaller? What is it? Somewhat bigger. %53% does it. You can do the arithmetic. And this gives me, obviously, 5.3 times 10 to the minus 3 equals H30 plus min. So there we have, before we proceed with this solution for correct final hydronium ion concentration determination, I got my hydronium ion value in this box. It can't be smaller than this, and it can't be bigger than this. So there's my range. 5.3 times 10 to the minus 3 up to 20 times 10 to the minus 3. I just wrote 0.020 differently. Well, not a whole lot of data points in there. 5.4, 5.5, 5.6, blah, 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 till I get up to 20. It's in there someplace. You can proceed now with the arithmetic. Should you so choose, to your heart's content. Now comes the next issue. Writing these charge balance equations, we've now recognized how to do that. But how is it, or when is it, I should say, can we take a charge balance equation and set it equal to a charge sum? The cases we have so far considered have allowed us to set the charge balance equation immediately equal to a charge sum by understanding the information given us by the label on the bottle. That's what we've so far recognized. For example, in the iron nitrate solution. The nitrate ion is in there at a molarity of 0.030, and it doesn't have its presence affected by pH at all. So that's a fixed molarity that tells us the charge sum. Aluminum sulfate solution, same thing. Sulfate ion is such a feeble base that the total molarity of sulfate ion in the system is the charge sum. Total molarity times 2, because of the charge magnitude 2 that you have to multiply by. So I've written here, if solution contains principal species, which are molecules and or ions, okay, which react to produce ions from molecules or molecules from ions, because whenever this happens, in the first case I'm converting charged species to uncharged species. In the second case, I'm converting uncharged species to charged species. Each of these transformations affects charge sum. For either of these cases, I cannot immediately set charge balance equal to charge sum, unless I know the extent of these reactions and or the K values for these reactions. Getting complicated, isn't it? But it isn't difficult. It's just some more information that you have to process. And you are quite capable of processing this information. So let's talk about the information and talk about how to process it. First case, in the notes, 0.10 molar ammonium cyanide solution. Well now, we'll start with the principal bronze-settlari acid-base equilibrium reaction in this system. You know how to play this game. Because for each and every system, the first thing you do all the time is PSI. Because if you don't know what's in the system, forget it. And ammonium ions are stronger acid than water and a principal species, and cyanide ions are stronger base than water and a principal species. So there's our principal Bronsted-Lowry acid-base equilibrium reaction. Now look at the acid-base table. To what extent do you expect this reaction to go? Large, small, particularly small? If I say the extent of this reaction is about 50%, would you accept that statement? Yes. Why would you accept that statement? Because if you want to assess extent, you have to compare the strength of the reacting acid to the product acid, or the reacting base to the product base. I don't care which one. But let's compare reacting acid to product acid, because the Ka values are right there. We don't have to do any Kb calculation, okay? Ka ammonium ion, 5.6 times 10 to minus 10. I'm reading it right off the table. See, I see it right there. KaHCN, 6.2 times 10 to minus 10. Are you seeing these numbers? Yes. Are these numbers much different from each other? Not much different at all. If you compare KBs for the bases, you get the same comparison. So this tells us, generally speaking, this is a small extent reaction. But if I want to assess the extent, this thing's about 50%. So guess what? If I now, for this very same solution, again, saddle you with the responsibility of writing PSI, what will you write? Beside water, what will you write? PSI for this system. What will you write? You'll write all the components of that system, won't you? Ah! So now we're taking a look at a case where if you're going to write PSI, you better be careful about the chemistry. You've got to let the chemistry talk to you, and I'm trying to get you to understand how to let the chemistry talk to you. We're getting a better appreciation for what these K values mean. Okay? Now then, is this a reaction which converts charged particles to uncharged particles? These are molecules, aren't they? So if I write the charge balance equation for this system, which is simple, the only two positive ions are these. And the only two negative ions are these. So there's charge balance. Can I set this equal to charge sum? Could I call it 0.10? I hope not. Because this reaction, which goes about 50%, has converted this charged thing to an uncharged thing, and converted this charged thing to an uncharged thing. So whatever the charge sum is for this system, I can say for sure it compares how to 0.10? Smaller than 0.10. Okay? And given that this goes about 50%, would you be surprised if I tell you that the charge sum for this system is about 0.050? Isn't that half of this 0.10 number? Good. Well, now you're seeing more how to play the game. Now let's talk about another aspect of this system. How do I calculate the hydronium ion molarity for this system? Is this a difficult calculation or an easy calculation? Hint, this one's easy. Now comes the hard part. Because my bet is each and every one of you is sitting there saying, how the hell does he know this is easy? Well, let me show you. So that you too can know that this is easy. We've recognized by looking at nothing more than Ka-ammonium ion and Ka-HCN that this equilibrium reaction goes about 50%. Is that good enough? Which means its K value is about what? If I got two reactants and two products like this, and the reaction goes about 50%.
Oh, it's the hydronium.
What?
Never mind, sorry.
I want to know a gee whiz K value for this reaction. It goes 50%, you got two reactants and two products. Okay? I want to know a gee whiz K value. 1! Because if it goes 50%, the equilibrium concentration ratio of products to reactants, right? Going 50% has got to be 1 to 1. Because half of what you started with became products, right? So the polarities at equilibrium are going to be about the same. So the K's got to be about 1. There's nothing fancy about this. There's nothing fancy at all. This is beyond 8th grade arithmetic. But I know damn well it's arithmetic that you folks have not yet been programmed to do because you were in these stupid classes where you're pushing buttons on these damn machines and not understanding anything that you're doing. And it's not your fault. So now you have to sit here and listen to this crazy man in front of you, jump up and down and holler about all this arithmetic you should be able to do in your noggin. And it's not your fault. I'm trying to help you learn how to do this. But I told you what I do to those fools who mistaught you. Because they're making America stupid and I won't have it. I won't have it. That is a sacrilege, a real sacrilege. That ain't fair at all. You people are getting cheated. And I don't want that. Now then, tell me, Ka-ammonium ion, 5.6 times 10 to the minus 10. How does that compare to a K of 1?
Very small.
Forget it. Ka-HCN, 6.2 times 10 to the minus 10. How does that compare to a K of 1? Forget it. Kb cyanide ion, 1.6 times 10 to the minus 5. How does that compare to a K of 1? Forget it. Kb ammonia, which we've now used a number of times. Anybody remember it? 1.8 times 10 to the minus 5. Next to 1, forget it. So what does this mean? Because we're now, again, we're going further with allowing these numbers to talk to you and tell you what they mean. It means that the only reaction of consequence in this system is that one. Which means for this system, based on our understanding of the magnitudes of these K values which we have just discussed, because they're the K values for all the species in the pot that we're concerned about, is that for this system, these molarities are equal. And so with these molarities being equal, after you learn how to calculate K for this reaction, which is easy, you write this. Right, that's K. What do I have to do to this K to be able to evaluate it? Will this work? Does this look like a game we played before? Well, now we're going to play it again. Look, ammonium ion, ammonia, hydronium ion, Ka-ammonium ion. Down below, cyanide ion, hydronium ion, uptime HCN. What does that look like? Molarity of HCN divided by the cyanide ion molarity, hydronium ion molarity product. 1 over Ka for HCN. Here we go. Done. So, we talked about the numbers. Let's put them in. Now you get out the pocket calculator and there's the value you get. That's pretty close to 1. Nothing fancy about this. So if we know that this is 0.90, and we know that these molarities are equal, and we know these molarities are equal, and we know each one of these started at 0.10, here's what we got. X squared over 0.10 minus x, quantity squared equals 0.90. Whoa, that's tough to solve, isn't it? What am I going to do to solve this? Well, I'm going to do this. Hell with this square stuff. And take this. And as soon as I get now the ammonium ion molarity as well as the ammonia molarity, then I can use Ka ammonium ion. Boom, calculate the hydronium ion molarity straight away. Or Ka HCN, because I'll now know the HCN and cyanide ion molarities. Boom, done. Now then, let me write one more solution on the board. 2 more. These are 2 solutions which are yet to be considered, and on considering these 2 solutions we will complete chapter 18. Now we won't be able to get to this tomorrow. Okay? But we will do this tomorrow. So I'm telling you right now, what you're going to tee off with tomorrow in the discussion gathering is chapter 19. That's what you're going to get. So you want to do yourself a favor, you read chapter 19 through section 19.3. That makes you ready for tomorrow's discussion part and makes you ready for the part of quiz 2 which will deal with chapter 19. Now, 2 comments on these solutions. You see what we did to solve this thing? This idea applies to this system. Solving for the hydronium ion molarity for this system is also a piece of cake. But solving for the hydronium ion molarity for this system, now that's more problematic. Because for this system, you've got to use charge balance and material balance, all of which will be revealed to you tomorrow.